Okay, next set of pages, we're going to talk about derivatives, tangent vectors, unit tangent vectors, tangent lines, secant vectors. Okay, and all those concepts, we will be computing derivatives, and the question is, how do you compute a derivative of a vector function? Well, the key phrase is that derivatives are computed component-wise. So I'll be taking the derivative of this, and this, and putting them in a vector. And then we'll talk about what that vector means when we do some applications. So this is an example of a problem you'll see. Given a space curve and a point of tangency, find a tangent line, find a tangent vector, find the unit tangent vector. So I'll define all these things. But maybe it'll help us think about this as the twisted cubic that we had last video, last lesson. So I'll just quickly share that again. See, we already had that guy up, so yeah. Okay, so here's our twisted cubic. That's the function we're looking at. We want to go when t is 1. Okay, so we're right here on that black dot, and we want to get a tangent line. And just like tangent lines back in R2, for y as a function of x, explicit functions, we'll have very similar definition, but it means the same thing. It's also a direction of motion, a direction of travel along this curve. Okay, so we'll come back to that visual in a moment. For now, though, let's crank away on some computations. So the derivative is done component-wise. So r prime of t is 1, 2t, 3t squared. So all the same differentiation rules that you've learned in Calc 1 help you here. This is a nice, easy polynomial one. And we want to do this at t equals 1. So let's first also, we're going to need this eventually, the point of tangency. When t is 1 was the black point on the CalPlot 3D visualization that we had. And that's when t is 1, we'll be getting this vector, which we think of it as either a vector or its terminal point. That's just 1, 1, 1. Or we can say that the point of tangency is at the point, if we write it in point notation, 1, 1, 1. Right? Okay, and then the derivative evaluated at that point. 1, 2, 3. That's a vector. And this is our tangent vector. And if we normalize it, make it have length 1, we get a unit tangent vector. So that's just going to be r prime of 1 divided by its length. So we need to get the length of this vector. That's the square root of the sum of the components squared. So 1 plus 4 plus 9, 13, 14, square root of 14 goes down here. 1 divided by square root of 14 times the vector 1, 2, 3. That takes this vector, shortens it to make it have length 1. That is our tangent vector, and we're going to plot some of these in a moment. But what we'll see is that along our space curve, that twisted cubic, we're going to stop at a point, and the tangent vector at that point gives us the direction of motion in traveling along that space curve, which again, if the analogy I like to use from Calc 1 is if that space curve is a roller coaster now, if you were to derail precisely at the point of tangency, you would fly off in the direction of the tangent vector, or which is the same as the direction of the unit tangent vector. Okay, let's do a little more analysis and algebra and cranking away at the calculus before we go back to the tech tool and visualize this. So it said find the tangent vector. Okay, we've done that. We've also normalized it, made it a unit tangent vector. How about the tangent line now? So we have enough information to do this because from chapter 1, we know how to create tangent lines, which are linear space curves. And so we need a point and a direction of motion. We have both of those things. The point of tangency, we have the direction of motion. Either one of these, the book get us to the same place. So the tangent line is given by the space curve, which is a linear space curve. The point of tangency plus parameterizing the vector of motion. which can also be written as 1 plus t, 1 plus 2t, 1 plus 3t. Okay, so let's go ahead and take a look at this. We should have the visual in our head, what is in front of us, the twisted cubic, the point of tangency, the tangent vector, which extending along that and making a line creates the tangent line. Now let's check if what we see in our mind's eye makes sense with our tech tool. Okay, back to our twisted cubic, and let's add our tangent line. That's another space curve. So change the preset 1 to 1 plus t, 1 plus 2t, 1 plus 3t. And let's just say from -4 to 4. See how that does. Let's make it a constant primary color. Okay, so our tangent line is in blue, our space curve in red. Let's make sure that they intersect at the black point of tangency. Yep, and they just touch. Cool. Okay, so let's see some other features in CalcPlot 3D. Let's see. Oh, let's put, we forgot to put in our tangent vector just to show that that also lives along the blue line. So we will enter a vector. The initial point is the point of tangency of 1, 1, 1. That's the point when t equals 1. The tangent vector was 1, 2, 3. Let's maybe change that to green. Okay, so let's see that the green vector does live along the blue line. In fact, you can kind of see the colors together there, or maybe take off the blue line for a moment and see that that is the direction of motion. It originates at the point of tangency, and that's the direction you would move if you were on a roller coaster and it derailed right there. You'd sail up that way. Okay, and then, oh, right, so back to I was going to show you animating some things on this, the original space curve. So this little gear shows you your different settings and some things you can add. So the trace vector, we talked about that last video, but let's just show that quickly. That blue vector is showing that as I move along, it's showing the what the vector r of t looks like as a vector rather than looking at it as just its point. Those are two useful ways of thinking about a space curve traveling as t moves across its domain. It's either this blue vector through space or the black curve moving along the red space, the black point moving along the red space curve. Okay, but let's turn that one off. Let's look at the tangent, the unit tangent, right? So that was our normalized unit tangent vector. That was the green vector that we'd shown, but we're going to see how it looks over time. That's what it is right now at the point that we are given. Interesting was at 1. And there is the point of tangency at 1. The purple vector is the tangent vector, shortened to have length 1, right there. And you can look at that animated over the entire domain. And again, notice at different places, it's where you'd sail off. Sometimes that's almost exactly the same as the curve, depending on the shape. Okay. And was there anything else at this point we're ready to animate? Okay, we'll get to the unit normal and the osculating planes in a bit. Normal planes. Oh, maybe the TNB stands for tangent, normal, and binormal. We're going to talk about the tangents and the normal. We haven't done the normals yet, but right now you know about tangent vectors. And so this will show just that's if there are multiple vectors in here, like the tangent and the normal, it'll show which is which with the label. That this purple one is our tangent, T for tangent. We only have one, so we don't need that label, but it can show you the equations. So this is the equation of the tangent vector at the point given. So let's enter the point of tangency we are looking at. 1, 2, 3, I'm sorry, at the point of tangency t equals 1 is the point 1, 1, 1. The tangent vector was 1, 2, 3, but we normalized it and got 1 over square root of 14 times 1, 2, 3. Well, if you actually do those decimals, that is what is shown here. The tangent vector is 0.27 in the first component. Remember, I is your standard unit vector 1, 0, 0. So this is just saying the x component is 0.27, the y component is 0.53, the z component is 0.8. And so you can, any point on this graph, as you animate those tangent vectors, the top line for us is the one we're interested in, and it will give you the exact equation of the unit tangent vector there. So it's another nice thing that CalcPlot3D we've used mostly for visualization, but here's an instance where it can do some calculating for us. Okay, so that's the first few vocabulary words we needed to know about how to compute derivatives, what they mean when you compute that derivative. You're actually getting a tangent vector, which you normalize to the unit tangent vector. But where does that actually come from? So let's maybe back up a little bit and think back to some things from Calc 1. Okay, so now we're on the derivatives of R of t page. And this was, again, just showing that what we just did, derivatives are actually computed component-wise, no problem. But where they actually come from is from secant vectors. So at the bottom of the page here, this is showing a secant vector. A secant vector, just like a secant line back in R2, connects 2 points, in this case on a space curve in R3. Connect those 2 points and you have a secant vector. Well, what happens if the secant vectors shrink and the 2 points between the secant vectors get closer and closer to the point of tangency? Well, that's when you get, flip the page, the limit definition of the derivative for a space curve. This is just an extension of the limit definition that you learned about in Calc 1. And you're going to let the secant vectors, the distance between the 2 points on the secant vector get smaller and smaller, get closer and closer to the point of tangency. Therefore, the secant vectors converge to the tangent vector. And that's exactly the same thing as the limit definition in R2 that you learned in Calculus 1, but it's applied component-wise. So you're really taking a limit definition of each component of your vector function. And so that's why we do derivatives component-wise, and that's what they actually represent to us physically. So another term for us is the secant vector, no problem. Just as easy as it was in R2, it's very easy to get secant vectors. But we really just use those secant vectors more as a thought tool to get us to the tangent vectors. Okay. Let's do another example. Let's look at this function, t squared t cubed. And what we want to know now is what happens to R of t, which is just this plane curve. Let's make it simpler for us right now. It's the R2 vector function when R prime of t equals 0, 0. So the reason we're going to ask about this is think about how important it was to take a derivative and set it to 0 back in Calculus 1. We did that over and over and over, right? That was the heart of, we call those CPs, we use those to find extrema, we use those to find intervals of increase and decrease, concavity. It was the first step in nearly everything you did in Calculus 1. Well, what happens when you take a derivative of a vector function and set that to 0? Well, you're setting it 0 now as a vector itself. So in R2, we're setting it to an R2 0 vector, but in R3, we could have a 3-dimensional 0 vector. And we're wondering what happens then. So in this example, the derivative is 2t 3t squared. We set that to the 0 vector, which gives us 2 equations and 1 unknown. And so we're wondering, can we solve this? You can't always get a value of t that makes both equations true. In this case, we can. When t is 0, this is true. we solved this. So t equals 0 solves setting the derivative equal to 0 equation. And what happens there? So we'll see that here, when we're talking about plane curves and space curves, that setting the derivative to 0 enables us to find points that are called non-smooth points. So some more vocabulary, and non-differentiable. And we're going to graph these and show you what they look like visually, what it means to be non-smooth, but you probably have a sense just what that word smooth means, like a smooth curve through space versus maybe something that's jagged, has jagged points on it. So we'll see that visually, but for a moment, let's go back to that twisted cubic that we also had, that previous example. R of t was t squared, t cubed. The derivative was 1, 2t, 3t squared. If we tried to set that derivative to the 0 vector, which again is 3-dimensional, there's no value. You can look at that right away and say there's no value of t. I don't have to do any analysis. I know there's no way I can make 1 equal to 0. No value of t is ever going to make that statement true. So this point is this twisted cubic, which we already know, we've seen a couple times now, is smooth everywhere on its domain. So if t goes from minus infinity to infinity, everywhere over the domain of this twisted cubic, it's smooth. There are no jagged points. So non-smooth points are points where you're going to, again, sort of abruptly change. Those could be like absolute value points, right at the peak here. Discontinuities, the same sorts of things that made something non-differentiable in R2 happen here. Okay, so let's look at this simple plane curve just so we can visually verify this idea of smoothness. So back in CalPlot 3D, let's change our function to t squared t cubed. And it is a plane curve, so we'll set the z to 0. Let's turn off this trace, the tangent vector. All right, now we can get this overhead view. Kind of shows that exactly at t equals 0, when t, oh, that's the other thing, when t equals 0, so t equals 0 is a non-smooth point. And t equals 0 corresponds to the point r of 0, which in this case is 0, 0. So you can actually plug it in to get the point in point notation, which is the origin for us here. Another reason we say non-differentiable is think about riding this. If this was a roller coaster, you're riding in the forward direction here, along the direction of motion given by the arrows, you would sail off in that direction. If you're riding this roller coaster in the backward direction, you would sail off this way. So any points for which the forward and backward directions of motion do not match, they're non-differentiable points. Those are the same things that held back in Calc 1. So non-smooth, non-differentiable at places where the derivative is 0. Okay, so we got lots of vocabulary in this lesson. Oh, and you can be, if you're not smooth everywhere, you could be piecewise smooth. So like, for example, the one that we just looked at was piecewise smooth because its graph looks something like that. It's piecewise smooth here. And it's only when it gets to that point that's non-smooth. So that's another vocabulary. You're going to see piecewise linear, piecewise smooth, and those are easy to handle because you just take them piece by piece and you can still do all the analysis on those. Okay. Let's work one more example. I think that's all of our vocabulary. So just to go over vocabulary, make sure you got it in your head. How do you take derivatives component-wise? What's the derivation of the derivative? The secant vectors converge to the tangent vector. A secant vector connects 2 points on your space curve. As those 2 points get closer and closer to the point of tangency, those secant vectors converge to the tangent vector. That tangent vector gives you a direction of motion in the direction of travel along that space curve. If the direction of motion in the forward direction and the backward direction do not match, you have a non-smooth point, which is also non-differentiable. Non-smooth points happen when your derivative is equal to 0, if there's a t such that that happens. The tangent vector is given by the derivative, and you can shrink it to have length 1, and that's then called a unit tangent vector. Okay, that's it. So one more example. You'll see this problem, find any non-differentiable points if they exist. They may not always, like the twisted cubic had no non-differentiable points, it was smooth everywhere. So find if they exist any non-differentiable points for, and they'll give you a vector function. Let's look at this space curve. Let's see, 2 cosine t, 2 sine t, t, where t goes. They didn't give us a domain, so we can assume t is from minus infinity to infinity. Okay, well, the key term in this is non-differentiable. So non-differentiable points occur when your derivative is equal to 0. So we'll take our derivative. Oh, before we do that, let's look. Do you recognize this? So back in the first video of this section, one of our goals is to be able to look at something, recognize nonlinearity. Check. Second thing, is this a familiar surface that might have a name? We've talked about a few, the twisted cubic, the helix. This is going to be a helix, right? Because the first two components actually create a circle just in R2 or a cylinder in R3, and then the T makes that wrap around the cylinder and create the helix. So this is going to be a vertical helix because we're moving in the Z direction up this cylinder. So we have a vertical helix, and we're wondering if there's any non-differentiable points on that. So let's go ahead and take a derivative, set it to 0. And let's see, derivative cosine is minus sine, so minus 2 sine t. Derivative of sine is cosine, so 2 and 1. Are there any non-differentiable points on this? Is there any value of t that's ever going to make this equal 0, 0, 0? No, so none exists. And again, think about that visually. Go to CalcPlot 3D, pause the video, practice your CalcPlot 3D tech tool skills, enter this, and you'll see that this is this nice, smooth, everywhere helix. There's no sharp, jagged points on that. How about find, let's extend this then, find the tangent vector at, let's pick a point, t equals pi. Tangent vector occurs when your derivative evaluates to that point. So sine of pi, let's see, that's 0. Cosine of pi, let's see, that's -1 times 2. All right, now this would be another good thing to go to your tech tool, plot the space curve. We already had the idea it's a helix. Plot the tangent vector at the point of tangency. So what is the point of tangency when t equals pi? The point of tangency is given by evaluating the space curve at that point. So r of pi is, let's see, -2, 0, pi, or in point notation, -2, 0, pi. So you want to enter this vector with the initial point of the point of tangency, show that that is the direction of motion along the helix when t equals pi, and then check that CalcPlot's animation feature also matches what you've got. And then another good check, make sure you could write the tangent line at that point, pause the video, give it a shot, and then we'll do it right here. So the tangent line is easy because you have a point 2, 0, pi, plus you animate with the parameter t in the direction of travel, which is given by the derivative. And so enter this into CalcPlot 3D as your space curve, which is a linear one. It's easy to see linear in all the variables. Make sure that this linear space curve and the original space curve just barely touch. Tangier means, from the Latin, touching or kissing. They just barely kiss each other right at the point of tangency. So a couple ways to check your calculus. Okay, next time we will start taking higher derivatives and see what they mean.